I'll share a screen and I'll load up the lesson I'm going to be doing. But before we do that, we could do other things if anybody needs anything. Let's go with...
Could we kind of just go step by step through one of the homework questions?
Of course.
Just any of them, it's fine.
Okay, let me get power numbers. All right. Load up that file for now. Now, do you mean a power question?
One of the ones from the, the lesson 13 homework.
Okay, lesson 13 answers. Now, let me know if this does it for you. I could either go completely from scratch, or I could, explain and so on the steps that are shown on the page. So whichever works best. All right, give my computer a second to load up. I thought I had lost it all. I have a whole bunch of work I've done on this hard drive for this computer because I can't plug a USB memory stick in. And so there's a bunch of stuff on the hard drive that I thought for sure was lost, and I was having a little panic attack. But apparently things are okay. And I just need to let my heart and stomach realize that. All right, go. It's loading. So one of the key things that you're going to hopefully get used to soon is the idea that, if you have a device that's designed to use certain voltage, it's going to have a certain resistance that will allow a certain amount of current, and as a result, the device will use a certain amount of energy per second. It'll have a certain power rating, right? That's all means the same thing. And so the weird thing is that the easy example is to talk about rather than like the 10% reduction in the textbook example, but the easy example is to say, like, if you double the voltage, what happens? So you have like a 100-watt light bulb. It has a certain resistance designed to work with 120 volts to let a certain amount of current flow so that it uses 100 joules every second, right? Power rating of 100 watts. So what happens if you double the voltage? Well, two things happen, sort of. So the first thing is there's more voltage, which means there's more push on the electrons, which means that more electrons will flow. This thing's taking a long time to load up. So more electrons will flow, like double the number of electrons will flow. And you can look at that in Ohm's law, right? You actually get double the current. But then on top of that is that each coulomb of electrons that are flowing, like double as many are flowing, each one of those carries double the energy. So you get a double-double, right? So instead of 100 watts, this thing is going to get times 2 is 200, times another 2 is 400. So the light bulb would try to function as a 400-watt light bulb. It is concerning me that this thing is still trying to load. Oh, never mind. There's a screen I couldn't see. I tried to load them up too close together. It's asking me if I want to continue waiting, which I already was continuing to wait. All right, here we go. So is really any of them at all? Like, it doesn't matter which one at all?
Maybe sorry, could you scroll down a bit?
Yeah, of course, but I have multiple pages here, so there's 40, 41.
Maybe just the last one is probably fine.
The last one?
Sure.
Okay. So hang on now. This is getting into... I almost feel like I should open up the file to do with this, just so we can look at the questions themselves and you can pick one. Is that the issue? Trying to sort of figure out which ones?
Sure, yeah, sorry.
Yeah, electric power. All right, so can you still hear me there? I just plugged the microphone in.
Yeah, I can hear you.
And it's the same as before? Just whatever, or better?
Sorry, pardon. Cut out a bit. Sorry.
Sound sort of the same as before, even though it has the special microphone plugged in?
I guess, yeah.
Okay, I can hear you better, but I guess it's more for me at this point. All right, so here's the power questions. You know, you're told you have a toaster, and they give you a power rating and a voltage. And so as soon as you see that, you're thinking, okay, well, what's the missing piece that I can find, right? And they're going to ask you questions, but right away you can look at yourself and like, oh, if I have power or voltage, then I can find current because P equals VI, right? So that we can get the current, which is part A. And then it says, well, what's the resistance? Once you have the current, then you have the voltage and you have the current, so you can find the resistance, which is V equals IR. So let's take a peek at that solution where they gave us, like it says here, it gave us the power and the voltage. So right away, I'm like, oh, P equals VI, I can find current, right? Just plug numbers in, solve for the missing piece. Please get in the habit of starting with the main equation. Start with P equals VI, plug in numbers, and then just solve and get your answer, right? If you start trying to use like an I equals P over V equation that you had to look up, oh my God, you're going to be looking up things nonstop, and your head's going to explode because it's just too much. You got to just look at P equals VI and V equals IR as your standard equations that we're getting used to right now. Once you have I, of course, then now you can put I and the original voltage you're given in and figure out the resistance, right? Just by dividing. So does that make sense?
Yeah, sorry.
Okay.
I think 41 was the specific one that I was questioned about. Sorry, I asked for the wrong one.
Okay. Actually, you didn't ask me. You said any of them, so whatever. But here we go. So light bulb design for 120 volts, and they gave you the resistance, right? So if they gave you voltage and they give you resistance, you got to look at which you're given. Which of course you're given voltage and resistance. So on 41, I've got voltage resistance listed. And then it is asking for power, which is annoying because before you can figure out the power, you have to do something they're not asking you for, right? That's the trick in textbook questions. That's the common trick is like, they ask you for something, but really have to do something else first. And that throws people for a loop usually. But you gotta, if this is what helps you through it, right? Is you look here and be like V and I or V and R are given, and then you notice like to do with this one, there's an I value that would go along with those two, so V and R, so you can get I first. Once you have I, of course, power equals voltage times current. V equals V times I. Right, so that's part A, and then part B, they say what if the bulb is I changed it to 240. Did I change that prior to you? Do you guys know that was changed, or did I forget whether I changed that before?
Yeah, I was confused when I was doing the homework because our handout had 80 volts.
Yeah, okay.
And I didn't realize you changed it. So when I was looking at the answers, I had no idea.
Yeah, I apologize.
This makes sense.
So I modified the sheet to make it better, and then forgot to tell you that I modified it to make it better, and so that sucks. But at least when you look at the sheet, you look at the given information and be like, oh, it's 240 now, and then you could just do it as 240 volt. But really, you could do the question the exact same way with the other voltage. It's just that this one's more obvious. Remember, when I was talking when I thought the computer was trying to load the file. It's more obvious to talk about, if you double the voltage, what happens? Well, you get double the current, and then each current piece has double the energy, so you get a double, and so that's the numbers that I'll show here. We could talk about the 81 too, easily enough, but it's just so obvious to look at the effect when you're doubling. So that's why I changed it. So here's the 240 that I did instead of 80. So we've got voltage, and we know the resistance from the previous question, right? So we can look and see how much current will flow. And now it's obvious here. That's why I got circled in red there that it's double the current will flow, right? And then I noted there as well that each Coulomb will carry double the energy. And so, our voltage, our power rating in the end ends up being double current. Like this is actually, this current here is that 0.5 times 2. And then this voltage here is the 120 times 2. So you can really see that double going on there, right? You've got the 60 watts times 2 gives you the 240. And so this question's designed to be really obvious when you get to see it here, like the idea of how this works, right? And what happens. And so, if you try to use a device in Europe without a proper adapter, which is a transformer, which we'll talk about soon in the course, later on in the course. But you know, you're just hooking up 240 and hoping for the best. Well, your device is going to try and kick out 4 times as much power as it's designed for, and of course that's not going to go well. So C, ABC, if you wanted to construct a bulb that would use 240 properly and still give out 60 volts, what would you do? Right? So you want to design the bulb differently so that it actually gives 60 watts. Well, that's now at the part A all over again. You got your 60 watts that you want, you have 240, you can calculate how much current would need to flow, and notice that it's half as much current, right? Half as much current carrying twice as much energy gives you the exact same power as before, right? So the logic there is going to work out nice. So then you look at this and say, okay, well, the resistance would need to be 960 in order for that to happen, apparently. So the resistance ends up being, resistance was given as 240 originally, and then the resistance now is 960, which is double, I think, right? In order to counteract the double. If that makes sense. Do you need to see the 80 volt version of it? Like the 240 volt is much easier to explain and talk about because it's you know, double voltage, double current. Whereas if you go to 80 volt, it's kind of like, well, how much is that? That's a reduction by a certain percentage, right? So it's a little bit harder to, I don't know, see the significance of the result if you think of it that way. How are we thinking about this question? Are we good for it, or do we need more?
I'm not sure about other people, but I'm personally fine.
Okay. So if you did this question all over again with 80, it just wouldn't be as easy to say like double and so on, right? It would just be like, oh, reduction by 32%, and then another reduction by 32%, or whatever the number was. So yeah. All right. So let's well, yeah, is there any other ones you want to see or look at, go through together? Okay. Now the lesson I loaded to get started on, is that where we're at? Yeah, because we did solving combination circuits. Do we need to go through any of those? Solving combination circuits answers. Anybody need to see any of those? That's from before. We probably already talked about that one. Was it just the power one we need to go through, or this would be I guess maybe the first lesson from Tuesday? Anybody need to see any of those? Speak now or forever hold your whatever, you know. All right. Moving on then. So are we talking about this one now? Just you miss one. I miss one day, and then I've come back and like, where am I? What day is it? And then my computer explodes on me and it makes it even worse. Yeah, because so we covered electric power, covered the combination circuits, and then lesson 14 is the phi charges and fields. So yeah, here we go. So this brings us to the start, you know, the more official start of the actual 4U curriculum stuff. We've been looking at a good review that makes it so we can understand all of the things that we're going to be doing, but this is a little bit unrelated, actually, to be honest, the way this goes here. But I felt like we had missed some things from grade 11 that I wanted to make sure that you had experienced. I don't want someone to go away from Rita with a 3U and 4U physics credit and not know anything about electric circuits. That would be kind of embarrassing, right? So here we go, though. This is electric, gravitational, and magnetic fields, and is the new thing. So we're going to be looking at electric fields mostly at the start here. So I feel like I want to just double check something here. Electric field strength, charges and fields. I feel like there's a modified lesson, and I don't feel like this is the first one. What lesson did I just modify? Strength. Is that the one? Just bear with me for a second here. I just have to, this would have been done before the lesson started, but things went south on me. There's a lesson that's dedicated to the idea of like what the heck a field is. And this is probably it here. I just was thinking in my mind that the field, what the heck a field lesson is first, would be first. But the way I have it organized is, yeah, so that's the one that's ready to go. All right, let's just go with the flow then here. So we're looking at lesson 14, official start to this electric stuff. Okay, so electric force, we would have done in grade 9, obviously the idea of, electric, two negatives repel and two opposites attract and all that stuff. So let's just look at a little history here where Charles Augustin de Coulomb, that's where the name Coulomb came from, for Coulomb electrons, of course, right? Back in 1785, before Google, he found some things when he was studying electric charges. So, of course, we know that if either size of a charge was increased, what would happen to the electric force? Pretty obvious. If there's more charge, there's going to be more force, right? So he found that there was more force, and so you could say that the electric force is proportional to the, it turns out that it was the electric force is proportional to the size of the charge of each of them. So it's proportional to both of them. So if you double Q1, you're going to double the electric force. If you double Q2, you're going to double the electric force also. Okay. So basically what I'm doing here is I'm analyzing through the known, or the what was discovered in terms of the size of electric force and how it relates to the amount of charges, size of the charges. And then basically we're going to have an equation be very logical and understandable for electric force, rather than just be mysterious and like it was handed down from aliens or something. All right, so the other thing that was looked at was about the distance. So if you decrease the distance between the charges, oh, sorry, this is electric force. Sorry, the electric force would, right? Not if you decrease, but the electric force itself decreases as the distance from the charges increases. But it turns out it decreases by the square of the distance. Okay, the square of the distance. Okay. Not trying to cross those out, I'm trying to emphasize. So this by the square of the distance. So we'd say, oh, okay, that means that the electric force is proportional to 1 over d squared or r squared. Is actually, I think it's r, and most of the equations are either or, d or r, it's just distance or radius away, right? So that's called an inverse square relationship. So what you'd have is, one sec. Here, I got a call. It might be to do with the computer stuff. Hello? It is? Hi. Thanks for. All right, I'm back. That was, they were calling to help me, but someone else had already helped me, so we're good to go. All right, so so Coulomb's law, stated as an equation, looks like this. And I just want you to be able to look at that equation and say, okay, yeah, that agrees with what we said. It's proportional to this. The k value is the proportionality constant. So if you're looking at a graph of, what would it be? Force. I guess you would end up graphing force, and then down here would be Q1, Q2, and over r squared. So force is related to Q1, Q2 divided by r squared, and you get a straight line, okay? And that straight line would have a slope of k, which I really like to show this, because then the k value, you can picture how you could actually measure it. You could measure the charge values, you can measure the distance away, you can square the value, you can tabulate all this and graph it and see that you get a straight line, right? If you're actually physically measuring things. So the k value isn't a mysterious thing that no one understands. It's just the result. It's the number that relates the force that you're getting, the electric force of attraction or repulsion. When you've seen in grade 9, two objects repelling because of electric charges and two objects attracting because of electric charges. So all you'd have to do is measure the size of the force, measure the charges, measure the distance between, and provided you can measure all those things, you could do an experiment that would allow you to determine the k value for yourself. Okay, so the Fe, of course, is the electric force. The k value that I'm going to talk about in a second is the slope, right? So those are all just obviously very measurable things, the force, the charges, and the distance. The K value is the proportionality constant. It's the slope, right? It's the slope, right? So it's the slope of that relationship between force and the things that the force depends on. The force depends on the charges and the distance. Wow, distance squared. Follow me so far? So we end up with this equation, KQQ over R squared for electric force. The textbook, I have a vector sign over it here because I don't understand why this textbook isn't listing a vector sign. It is a vector. It's a force. Of course, it's a vector. They basically want you to think about what the direction of that force would be in the context of a question. You have to look at it and be like, well, if they're repelling, then it ends up being to the left in the situation, however it's drawn, or maybe it's to the right, or maybe it's whatever, right? But you have to decide whether it's repelling or attracting, and then decide the direction of the force as a result. So I have a note down here saying, to point out that if the charges are like charges, they'd both be positive, or if they're like charges, the force would be positive because they'd either be plus and plus, right? So if they're like charges, in other words, plus, plus, or negative, negative, either way, we end up with a positive, right? Because negative times negative does still give a positive. So basically, you can look at the result of the force, and if you want to think about it in a robotic mathematical way, then if your electric force is positive, it's a repulsive force. But you're still going to have to look at it and say, okay, so picture this. Okay, if this is Q, if this is the let's look at Q1 and Q2, and let's have this be a repulsive situation. So we've got maybe 2 positive charges or 2 negative charges. But basically, if you calculate Fe, it's going to be this. Right? It's going to be to the left. So the force of this is force of 2 on 1, let's say, Q2 on Q1, right? So see how that force is to the left in this diagram on Q1? When you calculate your value for the electric force, it's going to be a positive value. And then you're going to look at it and say, okay, so that means repulsion. And then, okay, so it's a force of repulsion on Q1. Okay, so that's going to be a force to the left. And so then you would actually list in, based on your direction system, you probably would have chosen a direction system previously to this. Direction system, you probably would have said this way is positive, right? And so you'd end up saying, oh, it's a force to the left. Oh, well, then we're going to actually list it as a negative value when we're doing the vector addition stuff. So I feel like I should run through that again. There's going to be examples I'll show you, but the numbers here would have been a positive and a positive here, and you end up with a positive result. Wow, no, I gotta flip my computer around so I can type it and write a little bit better. So we end up with this positive result. That's supposed to say. A little bit better. So that positive result would mean repulsion, but then, if that ends up meaning repulsion ends up meaning to the left, right? So i.e. to the left in this situation, I'm going to just say left in an example, like if it's to the left in an example, then you'd end up saying a negative value for this thing. So it'd be like Fe would be a negative number, right? So Fe equals, in this case, Fe equals a negative number. So once we see examples of this, that should end up making sense. The other version of this, of course, is if we're talking about an attraction situation. That's when you have opposite charges. So if we have opposite charges, obviously it would have to be a positive and a negative. And so that's actually going to lead to a negative Fe. And so that would be an attraction force, right? I should change my color of my pen that I'm using there just to distinguish. Let's go with like orange or something. So if we have opposite charges, then it'd be an attraction charge. Well, that would be a situation where we would have had, I'm going to go red, it's similar. So that would have been like Q1. Oh, it's still orange. Weird. Or no, it's red. I don't know. Is it? Q1, Q2, if this one's, say, negative and this one's positive, now it's an attraction force, right? So you can tell, obviously, based on the positives and negatives, it's going to be an attraction force, right? And so it's this way. And so, you know, I'm giving you the opposite examples because they're weird. Sometimes it'll work out where the positive means to the right. But in this case, the Fe equals KQQ over R squared would be a positive and a negative. So it's going to be a negative number, right? It says negative number there. It's just slightly overlapping that box. You're going to say, oh, that means attraction. So let me move that over. I can show it. I'll shrink it down a little bit so that it's easier to see. So that would mean attraction. Yeah, whatever. Seriously. Attraction. And then therefore in the diagram, right? Therefore it's like that. And then therefore Fe in this case gets listed as a positive vector. Because we're going to need to be able to combine these vectors, of course, right? Appropriately.
What's the difference between Fe and Fg, sorry?
Fe is an electric force and Fg is a gravity force. These are all E's on this screen. Are we talking about G's from previous knowledge?
No, like in the top left. Like it says where Fg equals, or is that an E?
These are all E's.
Okay, I thought it was a G.
Unfortunately, it's all just a little bit small there. So these are all E's. We're talking about Coulombs law. So it's of electric charges. I'm going to go E for there, like E electric charges. I'm glad you asked there because it's definitely not G's. Charges. Right, so this is an E. This is an E. Everywhere it's all E's. It's more obvious in my typing there, but where this originally came from, it's a little bit, the resolution's a little bit low, so I can see why you'd say that. Okay, so that screen looks great. Now, doesn't it? We'll do more examples. It'll make sense. All right, so let's get rid of, it still works. Let's get rid of these boxes here. Maybe not. Where's my keyboard?
Your mic's off.
There, we're good now, right? I don't know why that happened. Weird. I bumped it
Yep.
again. Okay, so we're good now. So this one's saying to compare gravity, you know, the universal law of gravity, with Coulomb's law. And of course, the gravity law is very similar, isn't it? So Fg equals gmm over r squared. And they end up being very similar because gravity, if you double the mass, you get double the gravity, either mass, right? If the Earth was twice as heavy, the force of gravity would be twice as much. If you become twice as heavy, then your gravity force will be twice as much. It's directly proportional. And if you go twice as far away from the center of the Earth, then your gravity, you know, it reduces by inverse squared, so it'll be 4 times less. So in comparing these two equations, the one you're familiar with already, the Fg equals gmm over r squared, we looked at it in grade 11 a little bit, and then in comparison to this new one, they're extremely similar. They're both inverse proportional to distance squared. They both have a very similar structure. They're both directly proportional to the charges. What does it say here? Directly proportional to the charges, whereas in gravity it's proportional to the masses. The proportionality constant K is much, much, much bigger than the proportionality constant G. So the K value up here was listed as 9.0 times 10 to the 9, right? So let's just point this out. The K value is 9.0 times 10 to the 9. That means 9 with 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is like, you know, what do they say the actual units are? It's like newtons per meter squared per coulomb squared. But basically, that's just think of the size of that thing, right? Versus gravity, if you remember, was 6.67. Then remember it, times 10 to the negative.
Negative 19.
19.
Close. It rhymes with the 7. It's the 11. The 19 was for the charges stuff. So this one is, you know, 0 decimal, and I'd have to go. Let me show you, remind you of this stuff. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 was where the decimal place is. So this is the number for gravity, right? So however many zeros that is, 0 decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I never try to just do, I always do this because I find it more reliable. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I think it was, I said 6, 6, 7. But of course I moved the decimal place 11 spots, and it, you know, of course, should be 10 zeros, right? So this one's very small. And this one's actually, you know, very large, right? And that actually equates to the gravity force is very small, right? Gravity force is very small, and in this case, the electric force is very large. So we previously have said, we talked about how gravity is the weakest force and so on, and I showed in class that it demoed like a small magnet can win a tug of war with all of the entire Earth. You know, this tiny little magnet can pull up a nail harder than gravity tries to pull it down, because, you know, we're talking about a strength that's in the proportional range of 0, 0, 0, 0, 0, 0, 0 business, in comparison to 900 million or whatever that number would be set as, right? So just be aware of, you know, the extreme difference between these forces strength-wise. Okay. So yeah, just fundamentally, electricity is way, way, way stronger. Electric forces are way stronger. But this is simple stuff for now. Remember, what's the magnitude of the force between two charges? It says between two protons separated by 1 millimeter. How much force is there between two protons separated by 1 millimeter? First of all, let's point out we're talking about a proton next to a proton, right? Separated by 1 millimeter. So we've got positive 1 coulomb next to positive 1 coulomb, or not 1 coulomb, sorry. The charge on a proton, not a coulomb. So we'll get to that. Okay, so here we go. We're given the charge is 1.6 times, there's that negative 19 business, right? So the 1.6 times 10 to the negative 19, it's not a coulomb of positive charge next to a coulomb of positive charge. It's just an individual fundamental charge, right? It's the same as a charge of an electron, 1.602 times 10 to the negative 19. They just have the 2 significant digits there. The R is in millimeters. Any instinct automatically on what you need to do there?
Convert it to meters.
Exactly. So divide by 10 maybe to go to centimeters and be like, okay, that's 0.1 centimeters, and then divide by 100 if this is easier for you rather than just knowing to divide by 1,000, but either way, right? So divide by 100, boom, boom, we got zeros, 0.001 meters. We need SI units. Always go to meters, kilograms, and seconds, because the electric force, the equation up here, electric force, this is in meters. Notice this M in here. It's not millimeters in there. That 9.0 times 10 to the 9 is calibrated based on meters. Even newtons. Newtons is force, which is mass times acceleration. So that's actually this Newton right here is, let's go green. That Newton right there is kilograms meters per second squared, right? So if you were to like put the K value in fundamental units, it would be what? Kilograms meters cubed per second squared coulombs squared, right? That's the actual fundamental units of that proportionality constant. They just put it in newtons because it's easier to look at. Anyway, so we want to know the electric force. Well, obviously we use the electric force equation, we plug in the numbers, and we calculate. Okay, so they put the number as this one, this number here. They put it in as 1.0 times 10 to the negative 3. That's the same thing though, because if you look at 1.0 times 10 to the negative 3, then you just see, oh, I'm going to move that decimal place 1, 2, 3 spots. So there's the zeros that fill in. Zeros are 1. Okay.
Where did the 1.6 times 10 to the negative 19 coulombs come from?
That comes from knowing the fundamental charge. And so let's make a little note about that. Protons, so proton charge, equals the positive of electron charge. And remember, the charge on an electron is known to be, so it's a positive version of the 1.602 times 10 to the negative 19. So that's what people refer to as, remember I talked about when we're converting between number of electrons in a certain number of coulombs and so on. I recommended that we commit to memory the 1.602 times 10 to the negative 19 number because it is the fundamental charge, right? Anything that's called fundamental tends to be the one you want to remember. So that the fundamental charge in nature, the smallest charge you can have is 1.602 times 10 to the negative 19. So the smallest positive charge, the smallest negative charge, on a proton and an electron respectively there, is 1.602. So that relates to that conversation we've had in the past about the fact that the universe is actually quantized. Things aren't as smooth and fluid and can be any value they want as it seems. You can actually only have more or less charge in a specific lump amount, and that lump amount is the 1.602 times 10 to the negative 19. Alrighty. So those numbers, fire into your calculator and work out as a value. Now, I feel like maybe I might want to go on an adventure here, technology adventure, and see if I can help you with calculations a little bit, because you're going to want to be able to do these calculations without it causing you too much grief. How are you feeling about using your calculator for doing these calculations? Are we good with it, or do I need to give you a little bit of demonstrate at least anyways that it can be easier than maybe you think? Who feels they want a little calculator help? Anybody?
I think we're okay because we talked about it in math a bit.
Okay. I was starting to plug in the document camera, but if we don't need to, we don't need to. Let me just, we're probably good then. Just use your.
I would like to see it.
Okay.
Yeah, me too, please.
Fair enough. Let's do it then. All good. So power's on, camera's on, and I just need to. There's my calculator. Not that. All right, so I'm gonna go up a little bit and over a little bit. And there's my calculator. Now let's see if we can see this here. So you can even see the screen and everything. All right, so I just need to move things around here a little so I can see numbers. So I don't know if I can be able to. Can I shrink this thing? Move slow. I don't know if you can shrink it. Okay, so just maybe feed me numbers and I'll show you how to type it in. But so on my calculator here, I'm going to do 9.0. Obviously, I didn't need to do the 0.0, but there's my 9. And then I'm going to do e to the 9. Okay, on this calculator, that means 9.0 times 10 to the 9. You might need to explore what that looks like on your calculator, but you definitely want to use an e to the 9 rather than times 10. You don't want to do 9 and then do y to the x. So if I said 10 y to the x, oops, I'm turning so you can't see it as much. 9, that does give me the 10 to the 9. But the problem is if I try to do 9 times 10 y to the x 9 business, it works, but if I were to do a square at the wrong time, like it doesn't use bed mass as easily. There's a reason the EXP button exists on this calculator. There's a reason an EE button exists on your calculator, maybe. There's a reason why on the TI-83 calculator, which I haven't used in a while. I'm trying to find, I'm just going to pull it out so I can show you. Where is, what do they call it again on this one? I haven't used it. No, here it is, EE. So just above, I don't know if you have a TI-83, but just above this one here, the second function button of that is EE. So that would look like 9, and then you do second and EE, and you say 9, and it gives me that 9. Trying to, so you can see it there, the glare. Here we go. You need to be over this side of the screen, right? So there's, you know, I had to spend a second there remembering, you know, how to use this calculator, and it's like that. There's second function E9, and that means, you know, times 10, 9 times 10 to the 9. And so I hope, I haven't used this calculator in a while, but I'm hoping if I say, certainly if I said enter and then I said squared, I'm squaring the 9 times 10 to the 9, right? So 8.1 times 10 to the 19. So I can demonstrate on here, if I said 9e to the 9, and then I said squared, see how it gives me the right number? 8.1 times 10 to the 19. So that's what I'm talking about. Whereas if you did 9 times 10 to the power of 9 and then just hit squared, that's probably not going to work, right? That's probably going to be squaring the 9 and then putting 10 to that power, and it's probably going to give me, oh, no, it did actually work. The TI-83s are pretty smart, okay? But on some calculators, you'd be squaring the 9 and then saying 10 to the 81. Oh my God, you're going to get an overflow error. It's going to be too big for the calculator to even try to do. 9e to the 9 squared also works, okay? This one here, 9 times 10 e to the 9 squared equals, and it's going 9 times, yeah, 10 to the power of 81. See how that's giving the wrong answer now. The bed mass didn't happen the way we thought it would. So in this question then here, I need to move this over so I can see my numbers. You could probably feed me numbers too, but it looks like I can do it now. So I've got my 9e to the 9 number, right? And then I'm going to say times 1.6 times 10 to the negative 19 times 1.6 e to the 19 negative. Okay, so that's one of them. And then I guess there's another one because we got 2 protons side by side, right? So behind this screen over here, there's another 1.6 times 10 to the 19. So times 1.6 e to 19 negative, and you can do the negative in the opposite order there if you want. But that's times another 10 to the negative 19. Now I need to divide by 1 times 10 to the negative 3 squared. I tend to just do this, divided by 1 e to the 3 negative equals divide by another 1 e to the 3 negative. And it's giving me 2.3 times 10 to the negative 22. Okay, so every scientific calculator, if you have sine, cosine, tan that you're familiar with from grade 10 and 11 math, then you're going to have an EE or an EXP or some kind of button. Usually it's EXP or EE. Those are the 2 most common names. Anybody want to key their mic and tell me what their button is if it's different from those? There might be another one I should mention. That's all. I just can't think of it right now. So have you found an EE or an EXP button on your calculator? Yes? Anybody want to key in and tell me?
Yes, I have.
Okay, and it's working and you're good to go and so on. Okay, so that's just a little like I would do in class if I was there with you. I'd start punching buttons into your calculator and then I'd hand sanitize afterwards and before. Anyways, you know what I mean. Anyway, so we end up with a positive value here that indicates that it's a repulsive force. And again, if we were looking at a diagram where the repulsive force meant that the force was to the left, then we'd actually end up using it as a negative value eventually when we're combining it with other forces. Or if it was up or down, you know, you'd call it positive or negative, and when you're combining it with other forces. That's going to come up soon, like the next page. Okay, so far so good. All right, so calculate the net force. There's going to be some review of grade 11 stuff in what we do here, right? Net force means, of course, all the forces added up. So F net equals F1 plus F2 plus dot, dot, dot. Just all those forces added up, right? So it says calculate the net force on the middle particle. So focus our attention here on the middle particle and determine the net force, the overall force on that middle particle. So the idea is we're going to have to figure out the force of Q1 on Q2. The idea is F net, I'm going to write it out here, equals F, let's say 1 on 2, Q1 on Q2 if you wanted to be more thorough, plus force of 3 on 1, right? 3 on 2, sorry, because it's the middle one we want. So it's the middle particle that we're interested in, and that's why it's force 1 on 2, and then force of the third of Q3 on the Q2. So that's the idea of what we're doing, is we're going to figure out each of those forces and then add those up, get the net force. So it's in this kind of diagram eventually where we're going to want to say, okay, so we have a negative charge plus a negative charge, or whatever. The signs go in based on the direction system, right? So I might start us out on the right foot here too, by the way, and point out direction system. Let's claim one, and let's call this positive. That's just what we kind of always do, right? So, obviously it's going to say here, you're given all these things, you're given the charges, and you're given whatever, right? So if you're looking at the distances and so on, you have to, use these. If I was looking at, I'm going to make a note that we're not doing this question right now, or we can do it afterwards maybe, but if I was looking at the net force on Q3, then Q3 would have force of Q2 on it and force of Q1 on it, right? In which case we look at a distance of 0.3 meters for Q2 and a distance of 0.7 meters for Q1, right? The way this one's set up, the 4 and the 3 that you're given, you just use them. But sometimes you'd have to know, oh, I got to add those together to get that total distance, okay? I'm going to point out that we are talking about point charges. So in this question here, they're shown as spheres, but in reality, they're actually point charges. So it's always point charges. So you don't have to worry about the radius of that sphere to talk about the distances. You're actually talking about the distance from there. This diagram's not as good as it should be, right? You're actually talking about 0.4 meters is from the distance of that, like the dot to dot. So they should have their dotted line continue, all the way to the middle in each case. People just like to see the spheres so you can tell there's something there, because if there's just a dot, it wouldn't look like anything, right? It would just blend in with the dotted line. So center to center distances are what they're telling you there. Anyway, so we just plug numbers in. So if we're looking at the net force on Q2, they're going to show what? They're going to say force of 1 on 2 is what that one says to start out with. So just like our previous page, I'm not going to, go through the number, button strokes again here, but the the K value, the charge, individual charge value, so the charge of 1 and 2, in order to figure out the charge on Q2, or the force on Q2, I should say. So I put in as a negative and a positive, and you've got your 0.4 squared and so on. You gave us meters in the first place. And so we've got a negative value there, right? That negative value means what? That negative value means an attraction, right? So, and you can certainly look at this as like opposites, right? Therefore, it's attraction. But for the same reason that we have opposite charge, like the fact that we have opposite charges leads to that being a negative value. So it should mean to you, if that's a negative, that should mean an attraction, right? So because it's negative, you know that it's being attracted. Okay, so now we're going to look at the diagram here, and we're going to say, okay, the force of let's draw it in here. So we're going to draw in. This is the force of Q1 on Q2. Right? Force of Q1 on 2 or whatever. And you can tell in the diagram it's an attraction and so on, and so it's to the left, right? So that's what they're saying there, is it's to the left. I just want you to make sure you realize that the fact that this thing is to the left is not because of that negative. There's an in-between step, right? So it's an attraction, therefore to left. It's very possible that you're going to have a positive result at some point, and you're going to say, "Oh, that means an attraction, or that means an repulsion, and then that means to the left." And so you're going to be like, "Oh, so it's actually going to, kind of flip signs on us, right?" So let's keep going, see if that happens. I hope it happens in this example. It certainly does happen in one of the examples, and the homework is all worked out so you can follow it. Okay, but I've done this exact kind of analysis. So the next force, of course, we need is the force of 3 on 2. So I'll just jump back to the picture here for you. Force of this one on the middle one, right? 3 on 2. So we need the 5 and the 4 Coulomb or micro Coulomb. Actually, I better point that out. This U Coulomb thing. In the homework, I have it listed, but I will point that out here as well. In your digital textbook that is now posted, let me show you here on my screen sharing. General and files. In the general files section, there's a folder that says grade 12 physics text. And so in the appendices, see if I can load that up on the fly here. I was going to flip to the page, but I'm kind of flipping the page digitally instead. There we go. So in the appendices, we've got, it's going to be a little small to see. You're probably better off, obviously, loading it up, downloading the file and using it directly. This, will it get clearer? Yes, it does. All right, so we're looking for the list of all of the different prefixes, they call them. So I just have to search here to see. It's at the very, I know it's very near the beginning of the appendices. I already found it. The grade 11 physics textbook is nicer because it's right on the back page. They know you have to refer to it a lot. So they have it on a certain, like on the back cover page, to make it easy to find. Right now, I'm just going to flip to it in the paper book so I can tell you where it is. Appendices. Much easier to find things in person, of course. Where did it go? There it is. We're on page 774, Appendix C. So I have to go down a fair bit. But what page am I on here? 753, I need to go to 774. Where am I at now? 79, too much. Again, you're probably going to download a copy of this and it'll be a little more doable than this. 789, I do a 774, so I probably should just scan now. So I don't go too far with my mouse. Did I go too far already? Appendix C, we're close. Where are the page numbers? 776, 774. Did it. All right. So this is it here. 774. And we need to go to the one above this one. Table 2. This file's different than. Oh, there it is. It's in front of me. I just wasn't looking. So prefixes. So like a kilometer is a kilo of meters. That's 1,000 meters. That's familiar. We've got a centimeter is actually like 10 to the negative 2. It's 1/100th of a centimeter. The one we're looking at in this question is micro. This little U symbol. I'll jump back to remind you of this. Right here, they did a UC, right? And so basically, you need to look up in your textbook, or Google works too. So the trouble with that is you might not know what that letter is called, right? So what you would do instead, I suppose, I probably should have just done this in the first place. I just have this habit of, thinking old school, like textbooks and so on. But if I were to type in, I'm just gonna have to multiple things plugged in right now, so I don't have my keyboard plugged in. You would type in metric prefixes. Metric prefixes, and if you did like an image of that, it's going to show you all of them. So it looks like maybe this one would work easily. So there's the mu. It's micro, and it's giving you 10 to the negative 6. So you can look it up in your textbook, or you can use Google as well, of course. All the numbers there. Micro 10 to the negative 6. Nano is common later on too. Whatever. All right. So enough of that. This is metric prefix. Keyboard's still not working. Let's plug the keyboard back in. I wish these devices had more than 2 USB ports. That's my one request. They're actually really nice devices otherwise, but anyway, it's metric prefix. And it means 10 negative 6. So that kind of stuff will creep in once in a while. And again, just like before when we had the the surface area, cross-sectional surface area, when it gives you a gauge of a wire, there's nothing stopping you from just Googling what's the surface area, cross-sectional surface area of an 18 gauge wire. Here, what's the, now this one would be tougher because of the mu, but now that it's a metric prefix, you just look it up. Okay, that's the key there, is metric prefixes. Watch for that. Okay. Anyways, so that's where that 10 to the negative 6 came from in the numbers when we looked at those. Moving on here then, so all the numbers going for that one gives you a value of negative 2. What does the negative mean in this case? The negative means, anybody? It's attraction. I think maybe that's the same as what we said last time. Is that what we had last time? My memory fails me. With negative, there's attraction as well. Okay. This one though now, let's picture what we've got. We've got a negative value, which means attraction. And so in our picture of Q1, Q2, and Q3, we're actually talking about this, right? And so that actually means to the right. Okay, so this negative result means actually a force to the right. That's kind of weird, right? So I think that's why the textbook doesn't put a vector sign on here, because it's a little bit dangerous to think of it as, oh, it's negative, so it means to the left. The direction stuff very much depends on the charge orientations, whether the charges are to the left or the right of each other, and so on. Okay, so there's going to be a little blurb about that, right? Because it's negative, it's an attraction, and therefore, based on the picture, you can tell it's actually a force to the right. So all we have to do now is add those up, right? We're saying, oh, we're just going to add those forces up. We got force, the 2 forces added up. We've got a 0.675 to the left, added with a 0.2 to the, or a 2.0 to the right. What we need to do is we need to put this in terms of like this right here, right? That is the same as a negative force to the right. So in the next line, oh, they don't show it. Shame on them. So let's go, that's the same as equals a negative 0.675 to the right. Plus 2.0 newtons. The units in every single line, but we have to recognize that this thing converts to be this thing. I wish my negative sign was a little bigger there, but the keyboard does what the keyboard does, right? So that means we end up getting essentially a subtraction to take away a 0.65, giving us the result of 1.325. Okay, and then you're like, oh, so that's a positive result, so that's to the right. and you paraphrase your answer. Oh, the middle charge would experience a 1.3 Newton force towards the Q3 or to the right. So, you know, just calculating forces isn't that crazy. Certainly our original question was just what's the force? Boom. The extra complication comes in here where we start saying, okay, well, what's the net force based on some things? You know, this multiple forces. So then you have to start adding vectors together. This ended up being a one-dimensional. So I think I have written there somewhere as one-dimensional addition of and subtraction of force vectors. The scarier one for you, I think, will be combining all of your previous skills to do the two-dimensional stuff, and we'll look at an example of that next. Any questions before we go to the two-dimensional example? So everybody's caught that you have to be careful about the signs, right? This negative actually means an attraction, which in this case means to the right. Whereas in the previous case, the negative meant attraction, which meant to the left, right? Because it's this one attracting to the left versus this one attracting to the right. So this is a good question that they have as an example here. It sort of shows both kinds of cases. So you become aware of them. All right, so moving on. Here's a two-dimensional example. Okay, they want to know net force on Q1. And when you look at a question like this, it's not a bad idea to start out with just an obvious thing like, okay, so this Q3 is negative, that one's positive, and so we're going to get an attraction force here. Think of that as like F3 on 1. And then, and I really want to put a vector sign on there, and I don't see why I shouldn't, to be honest, right? It's just the idea of the vector sign on this one is the one that's sort of iffy, right? Moving on, we've got a repulsion force from this one, and you can start to try and think about it, but here, you know, you've got a larger force down here, but it's farther away, and then you've got a smaller force here, but it's closer. So I really can't tell the sizes of these at this point. I just know they're going to be these directions. So this is force 2 on 1, right? But certainly here the sizes, we can't really tell. We just know that there's going to be forces like that, right? We're going to need to add those up. To add those, what do? We put them tip to tail, right? And so we're going to do lots of nice little review of that as we go through this question. So it's going to end up looking like this. You're going to have this one, and you're going to have this one. I'm just changing colors more just to make sure they're separate pieces here, but leave it like that. You're going to have that one, and you're going to have that one added together, right? And so, you know, depending on the sizes of these things, we're going to have a resulting force in the direction shown there. Just putting them tip to tail, end to end, gives you like this F net, right?
Does it matter which one you put for the tip and which one you put for the tail?
No, I'll show you actually. Great question. I just have to regain control of my computer screen here. I don't know. I'm gonna try putting my mouse farther away from the computer or something. See if that, or maybe it's closer. I don't know. Still, there we go. I've got control again. I used to have to restart the computer to get control again, and I'd lose the file and everything else until I figured out that it was a Bluetooth conflict. Let me just put that there so I can rearrange. But if I put this one first and then this one, right? So I've got the red and then the blue. Notice that net force still goes there nicely, right? Because it's
Okay, thank you.
result. So, great question. All right, so undo that little move. So they have an answer here, sort of, but I think we probably maybe need to go through some numbers to it. But basically, it says use the equation to find. Oh, it says the equation. Yeah, well, okay. The force equation, the calculations that you can easily just plug into your calculator. It says the result is 247.5 newtons. Okay, and now it's a positive force. Let me just use my purple emphasis marker here. Oops, purple. I wanted purple. right? So because it's a positive, it's a repulsion force. So that's force 2 on 1, repulsive force, you can tell it's up, right? So yeah, I just wanted to make sure I was reading the right thing here. So it's up, right? As shown in the diagram below, but I've shown some stuff here already, right? So let's see what they have there. So, oh, they have a diagram way below, I guess. I don't know where their diagram is. Down here. Let's just go through this bit by bit. So I would still want to get the other, oh yeah, sorry. So undo here, just so I can go through this with you as a thought process. Now, you've already seen that it says Pythagorean theorem there, but why do we need the Pythagorean theorem? Because we don't know that distance, right? We don't know the distance between these. And so lots of little things will come in as a review for in these types of questions. And you just have to have the fortitude to go through and review those things from previous classes, right? It's a grade 12 level class that combines, some of the math from previous courses as well. So it says here, Pythagorean theorem helps you figure out the distance between the charges. And so they have it calculated to be, and then based on that distance, they found out the force is negative. So let's focus on the electric part first, and then we'll go through the Pythagorean theorem review if we need to as well. But they said they found the force to be this negative number, which means an attractive force, right? And so because it's an attractive force, they have it written as like towards Q3. You're basically going to say like down and on an angle to the right. We probably, we can really figure out those angles as well, even actually, right? Because based on the trig, we could get what this angle is here, and then based on that, we can get what this angle is there, call it angle X, eventually, once you figure that out. And we'd actually be able to say, oh, okay, so that's, right, and then X degrees down, right? And so they're saying here to get the angle. Let's see what they have written. I have a feeling I'll have to do this.
Mr. Horn, sorry, I have a question about like the picture above.
Sure.
How come like the blue arrow is going up? Like, is there a reason why it's not going down? Like, is it just because?
So the blue one's up because the Q2 and Q1 are the same charges. And so it's a repulsive force. And so Q2 pushes up on Q1.
Oh, okay.
Okay, and that, yeah, no worries. And that was back here. There's a lot of things, right? So absolutely ask away. So we've got this repulsive force. And so you look at the diagram and say, oh yeah, okay, so it's going to push it up, right? So they're saying here now to get the angle. Now, what angle are they getting there? Tan equals 52 over 30. 52 over 30 means they're getting theta. As I already labeled, actually, luckily it was theta, right? So they're getting that's 60 degrees. They're saying tan of theta equals opposite over adjacent, 52 over 30, and they're getting it 60 degrees. And so they ended up saying, okay, well then that one's a direction of it says to the right of down, or in other words, I would maybe write it as down and then 60 degrees to the right. That's the way you're going to be more familiar with having seen angles. But we did, of course, in grade 11 mention both ways. 60 degrees to the right of down means the same thing as what they showed. So the only thing that wasn't shown here, the tan was shown at least. Do we need to see the Pythagorean theorem part of it? Could just, obviously it's pretty quick to show, but this is L maybe. So this is L squared equals the 30 squared plus the 52 squared. Once I get the answer here, I'm probably going to convert it to meters. But obviously I get a value here of like the 900 and whatever and so on, and I root it and get a value. Okay, so then eventually I get like root of both sides. Oops, I'm going to do it here. Root of both sides, and I end up with L equals whatever that number was. They don't even have it listed anywhere because they used it as part of the their calculation. But again, we can still do that if you want. But just know that would have happened, of course, along the way, giving us an L equals a number, and then picture that this would have come from FE equals KQ Q over, in this case, L squared, right? The R squared is really the L squared. And that's where that number would come from. Okay. So it looks like now we have an actual size, 247 up and 96 down. So the up one is more than double. I didn't know at the time, right? The up one's more than double. I probably could have reasoned it out because the size here, you know, it's a lot different, but it's the distance between. There's actually something to take from this, right? The distance between being much larger here to get to this bigger one, you know, the distance between has a way bigger effect, and you should know why. Why does the distance between have such a big effect and make the force be so small, only 96? Because electric force varies with distance squared, right? So, you know, you go twice as far, it's like 4 times less force. So what else do they have for the solution here? They're going to talk about how we're going to draw a net force diagram. And so it looks kind of like either of these, only the lengths will be different now, right? So they're going to show here, they've got a large 247 plus a small 96, whereas mine was, you know, they're both just the same size. But this is a more to scale version of the diagram. And so to get that net force there, what would be your preferred method? I suspect they're probably going to say they're going to use cosine law. So grade 11 math review here. If you're looking for this value here of D or X or L or whatever we're going to call it, let's call it, what do you want to call that? What did they use? They might not have used anything actually ever. Let's call it, you know, R for resulting distance or something, resulting force. Actually, it's F, right? But anyways, so that thing there, notice we've got an opposite angle to it, and then we've got the two sides, right? So that actually means we could use cosine law and get the value. So that's doable. Cosine law is totally doable. That would be R squared would equal the, you know, it's always, I don't know if you saw it like this or not. I always teach it like this. It's always this one and this one are squared, and then it's -2 of those same ones again. And so in this case, we've got the 247 would be there, and the what is it? The other number is the 96. My pointer tools changed to a pointer mouse instead of a drawer again. That's all. Anyway, so this is the 96. 5. I'm just trying to give you a little help on how to remember the cosine law in the context of a physics class, because in a math class you've recently memorized it, right? And so you don't necessarily have. I suspect you might not have a way that helps you remember it in the long term. And so the way to remember it in the long term is if this is A and this is B, then this is A and B again, right? And then see how this, if we were labeling this triangle, actually, let me just redo that because I'm going to stick with the normal convention. Little a, little b, little a, little b. And so when we're labeling this triangle, this would be a little c actually, right? So that's a little c, and then the a and the b would be wherever they are here, A and B. And so I would have labeled this thing as a B and the A and the C. So sign convention and labeling in math is always to have capital letters for the corners, and then the opposite side being the matching little letter. And so this cosine law here, let me get rid of that R because it's in the way of showing you the pattern. So the R, that's supposed to be a C. So there's your C. What you get in cosine law is this will always be the opposite angle, the matching opposite angle. I'll just hard fill in a C there so you can see. So when I saw this with cosine law, it was easy for me because I noticed that I've got an angle and an opposite side that I'm looking for. And as long as I have the two other sides, I know I can fill in the cosine law. Okay, so that would be one way to do it. Or, so cosine law, that's great. Or you would use components, I guess, right? So you would do your component addition. And you would have the up component there. So our x and y components, we have an up of 247.5. And then we have an over a certain amount and a down a certain amount. And so we have to figure that out, right? So we've got the 96.25. And then we have the x component of that over and the y component of it down. And so that x component would have been from, if that is if this angle here is labeled as 60 degrees, so if this is 60, then this is going to be 30, right? Because it's 90 degrees. And so if that's 30 degrees there, then I can easily label this x component as, so this is like, F, the electric force of I think it's the 3 on the 1. Or looking at the x component of it, and then the y component of it. I just don't feel like writing FE 3 on 1 x component. It's it's a mouthful. So this should be easily done here as the 96.25 times cos of 30. And that'll give you the x component. So I'll need that value if anybody wants to calculate that. And then the red one would be the 96. The y component would be the 96.25 sine of 30. And so what I'm reviewing right now is that when you're adjacent to the angle, you use cos for the component. And when you are opposite, so the y component there is opposite the 30 degrees, right? Then you use sine. So I've reviewed cosine law and then the component version as well. Anybody have any numbers for me for things? I need a number for the x component. And I just have to fix something here too. Notice that I put an x component in as 247. Of course, that's a y component, isn't it? Because it's up. So there's no component sideways at all for the 247. Straight up. And then the other vector now has an x and a y. And so I'm going to put the x information in the x column and the y information in the y column. So I just need a number value for 96.25 times cos of 30. Not sure how I'm able to do that faster, just starting now then. It's 83.35. 83.35. I'd recommend having a calculator nearby during a physics lesson just so you can help out like that, keep things rolling. Times 30 sine, it's just going to be half of that thing, of course, 48.125. And then we add those up. So we have on this result here, picture this resulting vector, we have an x component and a y component of it. So the x component is going to be the 83.35 because of this. Those are our x's added up. And then I have to be careful here as to what direction things are. So I put the 247 in as up, and then the one that I meant to put in as red here. So it's going to be a little bit of a bugger to change. There we go. That's vertical as well, but it's down, right? And so I have to put it in as a minus. So I need to do 247.5. Take away 48.125. And that gives me a 199.375. So that's here, 199.375. 0.375. Squeeze that in a little bit. So obviously there you're going to do the Pythagorean theorem now to get that value, right? And so your end result here after doing components would be to do the Pythagorean theorem. So we're going to say that FE, or F net, let's call it, just to be clear. F net equals the root of the sum of the squares, right? So we'd have the 83.35 squared is just the end step of the Pythagorean theorem. Once you've done the Pythagorean theorem enough times in this way to find the hypotenuse, obviously just skip all the rest, the starting steps, and go right to it. So that is 83.35 squared plus 199.375 squared equals, and then root. So I'm getting 216.1 or so newtons. And then you look at your diagram and you say, okay, what direction is that? Well, you can look at, tan inverse of the 199 over the, so the angle would be tan inverse of the 199 over the 83. I'm just going to type in do the first numbers there as for writing purposes, but 199.375 divided by 83.35 equals whatever it equals, tan inverse gives me 67.3 degrees. So we should be seeing an answer of 216.1 newtons as a size and at an angle of what? We're going to say right 67.3 degrees up. Normally we'd say like east 67.3 degrees north, but I haven't been referring to east and south and west and north and so on in this diagram. So in this question, so they end up with, they're saying 171s. I might have made a mistake somewhere along the way. I was hoping it was going to be the right one, but what happened? I'd have to, basically the process is correct, and either they've made a mistake somewhere or I've made a mistake somewhere. But I maybe afterwards I'll diagnose and figure out where the error is. But for now, do you have any questions other than finding the error? So I suspect, I'm feeling some empathy for you that you're looking at this like, holy cow, like there are a lot of things that you've learned in the past that you're going to need to be able to pull out of the toolbox and use. I'm not going to demand that you use cosine law in a question where you can instead use components. Choose your own adventure on those, right? Sometimes if you ever did have a question though, where there wasn't a 90 degree in the result, well, actually components still work anyways. There are some cases where cosine law and sine law are needed. So you might want to just have a little review sheet of those handy and go through it and make sure you're on track with how to do that. Any questions right now? You can still hear me, right?
Yes, we can. There's just so many questions. It's hard to pick one.
Okay. So let's go through another question and step by step. And this one had some steps that were missing, but they're steps where you're just plugging, like for example here, to get the force. Where did that 247.5 come from? Well, it came from putting in these charges and this distance into the equation and getting the force, right? Which we've already done, enough times. In this question, they're skipped, but I don't feel that should be crippling. Same for the 96.25, like it's just plug in the values, right? So I did show how to calculate the length in order to know what to put in there for the charge value or the force value. And I put here, obviously you're doing the kq over r squared again. Once you do have those force values, it's an up and an over, and you got to add them up, and that's what this diagram shows. The up plus the down to the right. Yeah. So cosine law would give you the value directly. even if you did do cosine law, that's just giving you the size, right? You would still need to do this, right? So with even with cosine law, you still need to do this as well, right? So plus theta. You still have to do that theta analysis in the end in order to get the angle that that cosine law result would spit out. So whatever this result is, the same result should be spit out there. Still, I have to figure out why that didn't give me the right number, but anyways, I'll come back to that. Still looking at 247 up. I'll have to check and see what happened. I suspect maybe one of these numbers must have been wrong by accident. I don't know which one though. Oh, no, it's 96. That's fine. 247.
How come you use the 199 and 83 to find the angle?
So the 199 and the 83 are used to find the final angle, because that final angle is in this red triangle here, right? So it's the opposite and the adjacent to that angle in that triangle. Make sense?
You cut out a bit there, so I couldn't really hear.
The red triangle in the end here for your resulting vector, like this net force vector, notice that it's a right triangle, and we've got an opposite side to the angle I want. I want this angle in here, right? I want an angle in this triangle, not this angle, or not any of the other angles. I want the one that's in the triangle for the result, right? And so the opposite and the adjacent side are the 199 and the 83, or whatever those numbers turn out to be once I check them out. But yeah, that's what they've added up to, at least for now. So that's how you get it, to use that triangle.
Then what does the other angle represent? Like, is that something, or is that just a label?
This theta here,
Yeah.
that theta there, why did they use that one? What did they do? They use sine law. Theta is found to be 16 degrees. Oh yeah, okay. So they used sine law to get this angle here, right? Because then they were able to just say, oh well, it's that many degrees to the right of up. Whereas I was looking for the angle in here, mainly because I figured students would probably prefer to work with a 90 degree. So sine law, what they would have done is they would have said, oh okay, I know that sine of theta over the opposite side, which would be the 96.25, will equal another pair of sides and angles, right? So they're able to use this pair now, the one I'm highlighting with my mouse there, the 60 and the resulting size, right? So they'd say, oh, that's equal to sine of 60 over the resulting size they're saying is 171. I got a result of 216, but I suspect maybe there's a number of 6 somewhere in one of the solutions, probably mine. Anyway, so this solves, of course, to be theta equals, they're saying it solved to be 16 degrees. So there's even a review of sine law too. Whenever you have a non-right triangle, of course, you have to use sine law or cosine law if you're going to work directly with it. Our workaround for grade 11 certainly was to use components instead. And now it tends to be a pretty nice way to do it for physics people. But sine law and cosine law are always on tap as well to use once you get familiar with them. Again, or to review over it again and become familiar with it. If that makes sense. Does that help answer your question? Yes?
Yes, it does.
Okay. So just a request for the whole class in general. Before you go there. If you ask a question and I help, it's super helpful for me if you key in right away and say yes or no, or like ask another question or say that's good, thanks. Because otherwise I'm sitting here wondering if I've explained it well enough, because I can't see the nodding and the smiling and the crying, whatever might be going on. So go ahead there, someone.
Sorry, I just have kind of like a dumb question, I guess. But overall, when we're solving for like the angles and stuff that we're doing all this work for, like I'm just a bit confused about like what exactly we're solving for. Like what is it compared to the original question?
Yeah, so remember the original question had a force up and a force down, right?
Yeah.
And so we're looking for the result of those added together. And so in my original diagram, my net force looked like this green one here that you can see, right? So we just need to know what direction that's in, because net force has a direction. And so we're going to want to say, okay, well, what angle is that at? And that is the one I tried to solve for.
Okay, so is it kind of like how like in the grid 11, it's like the bearings and stuff kind of?
Yeah, absolutely. Yeah, so we know we end up calculating the actual size of the force up and the actual size of the force down at a specific angle, and then we need to figure out the resulting force based on those, right? And so yeah, we want the value of the force that this charge feels as a result of the other two charges, and we need to combine the individual force vectors in order to figure that out.
Okay, thank you.
Yeah, no problem. So yeah, the next one is this one. Okay, and so I just need to tell you something just briefly about what they'll use the term static equilibrium. So I'm going to use that term here as well, just to familiarize you with it. But you have two identical charged spheres hanging from the middle of a 0.8 meter string. Usually, often they'll say to you that it's a super light string. You don't have to worry about the mass of the string. It's insignificant or inconsequential. Says the repulsive electric forces between the charges is, I have to word that a little bit better, but basically they're being held apart by their mutual forces of repulsion, because we have these two identical charged spheres, right? So they're being held apart, and the angle between the strings at the top is 20 degrees. And then if the masses are 3 grams each and they have the same charge, I want you to determine the magnitude or the size of the charges. Okay, so that one seems a little bit weird to start out with, because you don't even know the charge values, right? You have a Q equals Q, fine, but you don't know what those are. And so you can't start calculating electric forces because you don't know the charges. Okay, so we're going to do this question bit by bit here. One thing to start out with, it's an 0.8 meter long string overall, and it's attached in the middle. So that means that's 0.4 meters and 0.4 meters. Okay, so that's one thing to start it with. Eventually, we're going to need to figure out the distance between these point charges. And so we could even just go ahead and do that right now if we wanted. That would involve cosine law. Okay, so that distance between, let's call it r, right? If we were looking at the distance between, reason I'm looking ahead and thinking, okay, I'm going to need to know that. So I guess we can just go ahead and calculate it, right? Because we're going to need to know it, obviously, because it's part of our equation to do with forces, with the forces of repulsion. So to start out with my cosine law, this is how I teach, or how I list cosine law when I'm teaching it. Right, to go along with the idea that there's this general form that you just fill in the blanks, and it becomes easier to do the more you practice it. And it's always going to be the angle and the opposite sign and so on, right? So since we know we have the 20 degrees, then we're going to put in the 20 degrees there, and then that forces the r value to be this one over here. Because I know cosine law and sine law can seem a little bit crazy, right? What goes where is hard to remember. So if that's the r side, then obviously these two sides are the other two sides, and then it's those sides again. So if these weren't the same, which they are, so we don't need to worry about it, but this 0.4 here would be again right here, right? And then this 0.4 here would be again right here. And I just need to add some brackets there to make that work mathematically. So that's cosine law for that thing. So we're going to do 0.4 squared plus 0.4 squared again. And then we're going to do, I feel like maybe I should do an in-between step here. So that, of course, gives me 0.32. And then minus, let's do the 2 times the 0.4 times the 0.4. Gives me minus 0.32. Did I? 0.4 squared times 2. 0.32. That's supposed to be 0.32, not 0.36, correct? Anybody following along? 0.4 squared times 2 would be 0.32. You gotta have to follow along because you have to help me fix little errors. All right. 0.3.
When you're using the cosine law, when you're solving for like a certain side, does it have to be a specific side? Like, does it have to be like the adjacent or whatever?
Yeah. So let me just finish this one sec here, and then I'll answer that question. Cos 20 is 0.9396 ... I'll keep a bunch of those numbers. Yes, the answer to your question is if you're looking for this side, right, then that forces you to have to use this angle, right? You have to have a cosine law where you're essentially using, if you're looking for a side, you have to use the angle that's opposite it. So right there, the side and the angle that's opposite it. Otherwise, you'll have a situation harder to solve, or possibly not even able to perform.
All right, that makes more sense. Thanks.
Good. All right, so thank you for confirming. That's great. So 0.32 here. Take away the result of that multiplication. That multiplication was 0.3007 ... And so we're getting the 0.32, take away that. So I'm actually going to, let me just show if I can here still. Is it still plugged in? Yeah, it's still plugged in or not. Well, I have a store button on my calculator. So I'm going to store that STO button. Stores that 30070168, so I have some extra numbers. I'm going to store that, and then I'm going to do 0.32, take away, recall that number. Anyway, so I ended up with r squared equals 0.01929 ... I'm not rounding the 9 appropriately even actually in that stage because I'm illustrating, I'm keeping more numbers. It's actually an 8 after that. Rooting both sides, I'm just hitting the root button of the big number, all the decimals. And the R value I'm getting right now is 0.1389 ... At this stage, this is a result for a length. And so because it was like a 0.8 meter string, technically there's only like one significant digit. So, I'd be comfortable saying either using the 0.1389, or I could use the 0.14, whatever is appropriate in the question. Or if there was 3 significant digits, if this was 0.800, for example, then of course I would have used, let me erase here, I would have used 0.139 if the whole question was 3 significant digits. Okay, so we've got the distance between, and so eventually we are going to be plugging into an equation where we like Fe equals K Q over R squared. And so we're going to be plugging a 0.139 squared into that equation, right? Eventually, like I keep saying here, we're going to have a number value for this, right? If we manage to get that number value, then the K value certainly is a value, 9.0 10 to the 9, no problem, and we'd have Q squared. So you see how eventually we're going to be able to solve for Q. Right? The trick is to get that electric force.
Sorry, is the K the number that we had from previous that we did a couple slides ago?
Yep. K is K in KQQ over R squared for electric force is always the 9.0 times 10 to the 9.
Okay, thanks.
So question is, how the heck do we get that electric force? So follow me here, okay? You are told the gravity force, right? So if you're told the gravity force here, or not gravity force, but you're told the mass, right? So if you know that's a certain mass, then picture how we know. Let me get rid of my cosine law help here because this diagram is going to be cluttered enough as it is. Right? So we got that value. The gravity force on this, we know there is one. Right? Fg equals, and we can even actually figure it out. We're like, oh, it equals mg. And so it's the mass of 3 grams. Of course, we're going to convert that to kilograms, right? So divide by 1,000. And it's 0.003. 1, 2, 3, yeah. So 0.003. And then times 9.8. Oh, I'm just squeezing it in. So 9.003 times 9.8 gives me that the gravity force on that very light little mass is 0.0294.
Sorry, why did we convert it from grams?
Always kilograms, meters, and seconds, right?
Oh,
So
okay, sorry, thanks.
no problem. SI units. We're early in a physics course, so please ask questions like that all the time because eventually it's just going to become obvious, but don't feel bad. Okay, keep asking. So we have a gravity force down of 0.294 newtons. So my next step is to take advantage of this. Okay, static equilibrium, I noted at the top, means that everything's balanced, everything's staying still. In other words, like there's no accelerations, which means that net forces are 0, right? So F net equals 0 everywhere and everywhere, anywhere and everywhere, right? So what you have then is picture there being a tension force in here, right? But we're not sure how big it is, right? So there's a tension force. So what we do know is that the upwards component of that has to balance with this. So I want to move this over enough that I can show this nicely. The beauty of digital work here. Right here, that is a net force of 0, right? F net equals 0. So F net in the y direction equals 0. That's what we're taking advantage of there. So basically, for that vertical situation going on there, those are the only forces that are vertical: the gravity and the component of the tension force in the string upwards, right? The electric forces, if you visualize them, they're just sideways. I'm not even going to draw them on here yet, but we've got a repulsion force this way and a repulsion force that way. That's horizontal, so it's not going to matter in a vertical question, right? And so we can, I think at this point, easily just sort of say, okay, so the tension force, or the component of the tension force up is 0.0294. It's matching the gravity. I will show the way I did in grade 11 as well. I need an eraser. I just need to shorten my tension down a little bit. So I can put the arrow on the top of that. And we're picturing like a little triangle there, right? A component triangle. But that's certainly the tension force, and we need that tension force. But for now, what we know is that F net in the y direction is 0. So let me give myself some room here. F net in the y direction is 0. I'm going to put it that way. And I'm going to point out that, of course, it's the gravity force plus the y component of the tension force. Okay, so I'm going to give myself a little bit of separation there, some white space between the two. Okay, so let me just put a star here and corresponding star there, because that's what's leading to that. So this leads to 0 equals the negative 0.0294 plus FTY. When I add that number to both sides, I get my tension force Y component is 0.0294. Right? So you can tell that's obviously up. I don't necessarily put directions in the context of a question like this. I have the diagram that supports it and so on. So I wouldn't necessarily be expecting that from you either. So we've got a tension force up. Okay, here's the next step that's It's seems a little tricky, but so we're going to use this to get FT, right? To get the tension force. So all we're going to say is, go ahead.
Like to get the X tension force?
We have the Y component, and we're going to use the Y component to get the actual tension force, the purple one.
Okay, the total. All right.
Yeah. So what we can just say is FTY equals what? So in this question here, how would we figure that out, right? So let me just redraw a little bit bigger and, whatever, so you can see it. FT is not even necessarily bigger, but it's out of the context of the question we were originally at there. So FT and FTY. And of course there's like the rest of the right triangle there and so on. But we're going to need to figure out this value. So we got to figure out some things, right? So basically, if I can get this angle, then I'm going to be able to say in here FTY equals FT, and I'm this is the 90 degree here, right? So I'm adjacent to the angle, right? So FT cos theta. So if I have that theta value, then I can fill in numbers in this equation. I'm going to have the 0.0294 filled in. I'm going to have the cos theta filled in, and I'm going to be able to solve for the tension force. Okay. So often, if someone's looking for FT, like looking for a tension force value, you're going to want to like have an equation that says FT equals. But it's much easier just to focus on the thing that you know, right? The thing you know is how to get a component. So you're like, oh, FTY component equals the tension force times cos of theta. So we just have to get that theta value. Is it obvious what the theta value is? So up here, this thing's equal masses dangling. That means that this is going to be divided into 10 and 10, right? That was actually key here, that these are identical charged spheres. That means that this angle is actually true. So this is a little bit of a special case, right? Like I can't just throw questions at you willy-nilly. You'd be like, oh, this one's 0.2 grams, now one's 0.6 grams. You'd be like, okay, now they're going to be hanging kind of lopsided, and it wouldn't be a very doable question, right? This is much more doable because it's a little bit special. That 10 degrees there, do you see the parallel lines theorem Z pattern working? Right? So I've got a Z pattern. Let's go with highlighter. Let's go with Z pattern. Oh boy, that's too thick. Can I change it to be thinner? Right, that's a Z pattern. That's not working for some reason. I don't know why. It's because the highlighter is trying to like form straight lines. But Z pattern, that means that is 10 degrees. Okay, so let me go back to my regular pencil here. 10 and blue. That's 20 degrees. 10 degrees, sorry. The original was 20. So cos of 10. So that means we can solve for the tension force. So I'm just going to do 0.0294, and I'm going to divide it by 10 cos of 10, right? So I'm getting the tension force in the string to be 0.0298, barely different. But that makes sense really if you're thinking about it. 2.85. I feel like I want to keep more numbers there at this point, just because it's so close to the actual X component. But it would round to 0.299, I suppose. But I'm going to keep some more decimals. So now I've got the tension force, and then we're going to use this to get the X component. So if you look at the diagram, that's going to be the sine of theta, right? So that means I can use my decimal 0.2985, which is in lots of detail in my calculator still. Sine of 10. So I'm going to get the X component of that force. And the reason I want to get the X component, just to help you picture this, is remember we talked about the electric forces are sideways. So we've got an FE here. And we've got an FE here. Those are x components. So transferring to the x component, that's going to allow us to work towards getting the electric forces. So 0.029 blah, blah, blah times 10 sine equals, so I've got a x component force here of 0.00518.4 dot, dot, dot. If I kept more, great. Whatever I end up keeping, it doesn't matter. Dx. So we're super close actually to having the answer, because all we have to do now is realize that the acceleration in the x direction is also 0. Right? Therefore, F net in the x direction is 0. So F net in the x direction is 0. That means that at the spot where I was looking right here, where I've got my, I've got an x component force and I've got an E, we've got a, right here, we've got FTX balancing with FE. So I think we can cut to the chase and say, so FE equals FTX, right? Which means that this value right here can go right there. Oops, almost.
Sorry, how did we get that the FTX equals FE?
Because we know that there's no acceleration, right? Sideways, it's a static equilibrium conclusion again, right? We're not moving, there's no accelerations. That means that the force is, let me go up to the top here, the force is sideways. We've got an x component sideways and we've got a repulsion force. Those have to be balanced in order for this thing not to be moving.
Okay.
So what was in between there was to recognize that the tension or net force was FTX plus FE, which leads to, of course, this, that they're the same as each other. So now I can actually finish this question. I can go up and I can say, okay, I've got my 0.005184 number in for this, right? Equals 9.0. I don't want to move things. I want to draw still. 9.0 times 10 to the 9, that's the k value, q squared over the 0.139 squared. That's just an equation to solve, right? So I've got my 0.005184 number. I'm going to multiply it by 0.139 squared. I'm going to divide it by 9.0 e to the 9, and I'm going to take the root. And I end up with a q value of 1.05 times 10 to the negative, I have to count numbers here, 1, 2, 3, 4, 5, 6, 7, 10 to the negative 7 coulombs. And that is the answer. Okay. So I kind of hope that you are going to watch this video lesson 7 more times or whatever you need, going through these steps, and following along the logic and reminding yourself of all these little things that make sense to do. If there's no acceleration, then net force is 0. Therefore, you can figure out balance forces, right? And so on. So that one was done super thoroughly, step by step. I feel like the one before it here, I'd almost like to have done it just from scratch instead of trying to make this page work. Let me know what you need next time around. We can maybe go through that one in full. Maybe I'll just do a video of myself doing it whenever and post it as well. But that is where we're at. That does involve, like, this is a big step up, right? This involves stuff from grade 11 physics and from grade 10 and 11 math getting all put together. And so it's going to be a little bit of a challenge, and that's why I'm being so thorough, and I got the video and the lesson, and there's a question in the homework, by the way, exactly like this one. Different masses, different charge values, different lengths, right? So when you try that question in the homework, this page and the video associated with it should be a lot of help for you, help carry you through it. And then you can see if you get the right answer, because the answer is actually listed in the homework and in the textbook as well. But so textbook wise, the hard copy, physical copy of the textbook is available at the school for you to go stop by and get. Otherwise, of course, you can use the digital copy of the textbook that is posted on the team site in where I showed you before, wherever it is, up here, general and files and so on. Okay. But you can arrange to go to the school and pick up a textbook if you want a paper one, of course. So that's not very.
You need to book an appointment or drop in.
Maybe just call the school. It's 359-5391. 359.
Okay.
Yeah, 359-5391. Just call them and ask what they prefer. I suspect you probably can just go. I don't know though. You know what? I don't know. I have no idea. I suspect you probably have to make an appointment, actually, come to think of it. But if I was to go, I'd just stop by. But I do have to actually ask for permission first, and the answer is always yes. I don't know. Whatever, right? So yeah, call, find out, and yeah, get a book if you want to use it. Otherwise, you can just, obviously right now, you can just load up the file. And if you notice in the files there, I did actually labeled them so you can tell, like we're talking about this one here, electric and gravitational magnetic fields. Be worse if you had to load up this one. So we'll keep loading them up and try to find the right one. But it's the chapters are listed there for you. Alrighty. So I hope that helped. Plug away at it, and it'll get easier as you tackle more and more of them. So there's another one just like this one. Plus there's the one that's sort of a little bit. There's the one that's a little bit new, and the solutions are there as well for you to learn from. Any questions right now? I'm not in any hurry. I know we're overtime right now, but if someone wants to ask a question, I'll help. It doesn't bother me a bit. Got a little bit of a late start because of the computer issue there, but everybody's good to give it a try?
Yeah, thanks.
Okay, you're very welcome.
I think so. There'll probably be a bunch of questions for tomorrow after we do the homework.
Yeah, absolutely, and that's fine. Email me questions too as you have them, and you know if anybody ever wants, I can do a screen share in the afternoon for whoever wants to get some help as well. So maybe monitor your phones. If you see a screen share pop up, it's because someone's asking a question. It wouldn't be a bad idea to jump on and say, "Ooh, I might want to piggyback on this and eavesdrop and hear what's being helped, what kind of help's being provided." But yeah, okay. But yeah, we'll do what we need to do to help you be successful. So ask away.
Thank you.
You're welcome.
Thanks.